It's likely that you've heard of the principle of energy conservation, the idea that in an isolated system, energy is not created or destroyed, but rather shifts its form like a pendulum trading potential energy for kinetic energy, or an atomic bomb violently converting mass energy into motion, heat, and radiation. And you've also probably heard of the principle of momentum conservation, the idea that if no external forces act on a system, its total momentum stays constant, so that the momentum before a collision is the same as the momentum after. This principle lies at the heart of fundamental particle physics. But have you ever wondered, where did these rules come from? Is there a deeper explanation, and if so, can it be explained in a way that feels intuitive and easy to follow? In today's video, I want to answer those questions. I want to show you one of the most remarkable ideas in physics, an idea that links symmetry with conservation. And I want to show you that the deeper reason for energy conservation lies in a very simple fact. That the laws of physics are the same today as they were yesterday and as they will be tomorrow. The laws themselves do not change in time. And I also want to show you that momentum conservation comes from another simple fact, that the laws of physics are the same here as they are over there. They don't care where in space you do your experiment. The link between symmetry and conservation marks one of the great breakthroughs in our understanding of the universe, as well as one of the most impressive stories of a young, brilliant woman trying to carve out a place in an academic world where very few women were allowed to succeed. This is the story of Noether's theorem. To begin, we need to understand what a symmetry is. When most people think of symmetry, they think of the symmetry of objects. For example, an equilateral triangle has rotational symmetry. If you rotate it by 120 degrees, it looks the same. A square also has rotational symmetry. If you rotate it by 90 degrees, it looks the same. And the same is true of other shapes like a pentagon or a heptagon, whereas a circle can be rotated through any angle and it still looks the same. But physicists are often less interested in the symmetry of objects and more interested in the symmetry of the laws that describe the dynamics of those objects. Richard Feynman gives a beautifully simple description of symmetry in his lectures on physics, quoting the mathematician Hermann Weyl. A thing is symmetrical if one can subject it to a certain operation and it appears exactly the same after the operation. This applies not only to shapes, but also the equations and laws that govern physics. Information lies at the heart of physics, and just like in quantum decoherence, where information leaking into the environment becomes practically impossible to reassemble, when your personal data escapes online, it can quickly spread across many brokers. Data brokers are companies that collect vast amounts of personal information about people. Things like names, past addresses, phone numbers, financial details, even online behaviour. They compile all this into profiles and then sell it, and once your data enters that system, it spreads across hundreds of sites, making it almost impossible to track down and remove manually. There are very real risks tied to this. Incogni's own research shows cases where data broker information has been used for identity theft, and people's search sites routinely expose home addresses and family connections to anyone who searches for them. It's not hypothetical, this happens at scale. Incogni helps solve that. They contact over 230 data brokers on your behalf and request that your information be removed, and they keep pushing back if a broker objects. It automates what would otherwise take hundreds of hours. They also have a feature called custom removals. If you find a specific website exposing your personal information, you can send Incogni the exact link, and their privacy experts will work to get that page taken down. So you're not limited to their automated list, you can target sites directly. If you want to reduce your online exposure, you can use my link and the code PHYSICS for 60% off an annual plan. And there's a 30-day money-back guarantee, so you can try it out risk-free. To see what it means for a physical law to possess a symmetry, consider Newton's universal law of gravitation, which says that the magnitude of the gravitational force acting between two masses m1 and m2, separated by a distance r, is given by g times m1 times m2 divided by r squared, where g is Newton's gravitational constant. Now, in order to determine the distance r, we need to introduce a coordinate system. Let's imagine a simple two-dimensional setup with an x and y axis, where mass 1 has coordinates x1, y1, and mass 2 has coordinates x2, y2. We can then form a right-angled triangle and then use Pythagoras' theorem to write r squared equals x2 minus x1 squared plus y2 minus y1 squared. And we can then sub this into our gravitational force equation. Next, notice what happens if we shift the x positions of both masses by some distance, leaving their y positions unchanged. In other words, we consider a translation of the following form: x1 goes to x1 plus a, and x2 goes to x2 plus a. We can label the shifted distance a on our diagram, and we note the x positions of the shifted masses. We can then follow the same Pythagorean approach to find the distance between the shifted masses, which I've labelled r'. We simply create a right-angled triangle, and as a result, our new force equation takes the following rather ghastly form. The good news, however, is that the a terms cancel, and the simplified expression is none other than the original force expression. And so, to summarise, we performed an operation, namely translating the entire system by a constant amount, and as a result, the form of the equation did not change. And so, according to Feynman and Weyl's definition, this is a symmetry, specifically a spatial translation symmetry. But we can also look at another symmetry of Newton's law of gravitation: rotations. Imagine rotating the two masses together about their centre of mass, so that their orientation with respect to the x and y axes changes. Although the coordinates of each mass have changed, the distance between them does not, and that means r stays the same, and so the magnitude of the force keeps exactly the same form. You can also think about this in another way. Instead of rotating the masses themselves while keeping their separation fixed, we could keep the masses where they are and rotate our coordinate axes underneath them. We could then measure the distance between the masses relative to the new x' and y' axes and determine the corresponding mass separation r', and we would find that the magnitude of the new force, F', has the exact same form as in the unrotated coordinate system. Once again, we have performed an operation, and after that operation, the law of gravity looks exactly the same. And so we have a symmetry, a rotational symmetry. Okay, so hopefully you now have a sense of what it means for a law to possess a symmetry. And for our purposes today, we're going to focus on two incredibly deep and profound symmetries relating to space and time. First, the idea that the laws of physics are the same in one region of space as in another. And second, the fact that the laws of physics are the same today as they are tomorrow or the next day. Think about it. The fundamental laws of nature governing the world were the same when Newton walked this earth and the fire of London raged, as they are today, and as they will be 1,000,000 or 1,000,000,000 years into the future. Yes, it's true, things change, but the laws governing those things stay the same. For example, consider the fact that we're currently hurtling through space as we orbit the Sun. In 6 months' time, our position in space will be very different. We'll be on the other side of the Sun, and the Sun itself moves through space as it orbits our own Milky Way galaxy, and the galaxy itself is moving through intergalactic space. But the fundamental laws of physics will not change just because our position in space has changed. And we can express this in mathematical terms by saying if x goes to x plus a, then the laws of physics do not change. And in terms of time translation symmetry, if t goes to t plus b, the laws of physics do not change. And so we have two very fundamental symmetries of the universe. And here is the absolutely crazy, mind-bending thing. It is because the laws of physics possess these symmetries that energy and momentum are conserved. And my objective is to now show you how. In order to do this, we need to refer to one of the most remarkable principles in all of physics. The principle of stationary action. Now, I've made an entire video on this topic which I encourage you to watch if you're not familiar with the idea, but let me briefly summarise the key point. Imagine throwing a ball up in a gravitational field. It rises, reaches its highest point, and then comes back down. And we can visualise this trajectory on a spacetime diagram with space on the y-axis and time on the x-axis. But why does the ball take this path? Let's consider the same trajectory again, but this time at each point along the path we compute the kinetic energy and subtract the potential energy. If we then add up these contributions over the entire motion, which is equivalent to integrating from the initial to the final time, we obtain a quantity called the action, and this is essentially the accumulated difference between the kinetic energy and potential energy along the path. If we plot the ball's trajectory again, then we see in the second plot the kinetic energy and potential energy curves, and the third plot shows their accumulated values. The green bar represents the accumulated difference between the kinetic energy and potential energy, which is the action. Okay, so let's plot the actual path again. And what we're going to do is mark the total action for this true path with a dashed red line as our reference. But now, imagine gently deforming the space-time path while keeping the starting and ending positions and times fixed. Each time we change the path, the kinetic energy and potential energy curves change, and their difference changes as well. And because the action is effectively the accumulated signed area between those two curves, the action changes too. And here's the remarkable thing you'll notice. For every deformed path, every alternative trajectory the ball could have taken, the resulting action is larger than the action of the real path. And so of all the possible paths connecting the initial and final space-time points, the path that the ball actually follows is the one with the least action. Now, technically, what we should say is that the true physical path is the one for which the action is stationary. In the case of the falling ball, the action happens to be a minimum, but in more general systems this need not be true. The action may be stationary without being the smallest possible value. And we can turn this into a precise mathematical statement. To see how this works, let's introduce our time and space axes once again, and then consider the true path an object takes between an initial position x1 at time t1 and a final position x2 at time t2. We can then schematically draw this path and we label it x of t. We then say that this is the true physical path if, when we make a small deviation of the form x of t goes to x of t plus eta of t while keeping the endpoints fixed, the resulting change in action delta s is equal to 0 to first order in eta. This condition, that the action does not change to first order under small variations, is what selects the true physical trajectory. Now, the quantity inside the action integral, which for this kind of system is the difference between kinetic and potential energy, is called the Lagrangian, and so we can write the action as the time integral of the Lagrangian. For a particle moving in one dimension under a potential v of x, we can write the Lagrangian as half mv squared minus v of x, where the first term is the kinetic energy and the second term the potential energy. Now, with this knowledge in hand, we're going to follow a wonderful and intuitive approach to Noether's theorem published in the American Journal of Physics in 2003. In that paper, they give a maths-light, highly intuitive route to the core idea, and it's incredibly informative if you want to develop a real feel for what Noether's theorem is saying. We will begin by considering a simple scenario consisting of a freely moving particle with no forces acting on it. In this case, the Lagrangian will simply be half mv squared, and as already mentioned, the action will take the following form. So let's now consider plotting a general trajectory on our spacetime diagram and zooming in on a tiny segment of the path. We then consider two nearby points along the trajectory, the first located at t1 x1 and the second at t2 x2. On such a short segment, we can approximate the motion by a straight line connecting the 2 points, and we assume that the velocity is effectively constant between t1 and t2. We can calculate this velocity by calculating the gradient of this line, which is simply the change in position divided by the change in time. And so we see that the velocity along this small segment can be approximated by v equals x2 minus x1 divided by t2 minus t1. Now, since v is constant on this short interval, it follows that the Lagrangian is also constant on the interval. Now, if the Lagrangian is constant along the interval, then when we consider the action integral, we can pull the Lagrangian outside the integral, since it's constant, and then if we perform the simple time integral, we see that the action can be approximated by L times t2 minus t1. And finally, if we sub in the expression for the Lagrangian, which was simply half mv squared, we end up with the following expression. The final step is to sub in the equation for the velocity, and we end up with an expression for the action along the short interval. This is the expression that we will use to approximate the action along a short segment in what follows. Okay, so let's now take the same short segment, but now let's consider translating the path in the x direction by some fixed amount a. If we label the translated distance on our diagram, then we see that at time t1 the path's new location is x1 plus a, and at time t2 it is x2 plus a. And we can then follow the exact same approach as before. We draw a straight line connecting the two translated points, and then label the change in time and change in position between these 2 points. And we then note that the change in x position simplifies because the a's cancel, and we end up with x2 minus x1, and so we can update our diagram, and so we see that the velocity along this translated segment is exactly the same as before. And so, because the velocity is unchanged, the kinetic energy will also be unchanged, and therefore the action will be unchanged. And so we conclude that as a result of our translation, the action for this segment does not change. We say that the action is invariant under spatial translations. Okay, but what is the link between spatial translations and momentum conservation? To answer this question, let's again imagine zooming in on a small segment of the trajectory, only this time let's assume that the trajectory represents the actual physical path of the particle. In other words, the path that makes the action stationary. With that in mind, imagine 3 infinitesimally close events along the trajectory at time t1 x1, t2 x2, and t3 x3. In this region, we then approximate the trajectory by 2 straight segments, which we label segment A and segment B. And our next task is to determine the action along each segment. Using the exact same approach as before, we can determine the velocity corresponding to segment A and the velocity corresponding to segment B. And then using the fact that the Lagrangian is constant along each segment, we can follow the same steps as before to write expressions for the action along segment A and the action along segment B. The total action for both segments will then be equal to SA plus SB, which results in the following beautiful expression. The question we now wish to ask is what happens if we apply a spatial translation to both segments? In other words, we want to consider the spatial translation x goes to x plus a. And we see that as a result of the translation, the x-coordinates of our 3 points have changed to x1 plus a, x2 plus a, and x3 plus a. We can then follow the same process and calculate the velocity for each segment using the translated x-coordinates, and we see that for the first segment, the a's cancel, and we end up with the same velocity we had before. Likewise, for segment B, the a's cancel as well, and we end up with the same velocity as before. This makes perfect sense, since the translation did not affect the gradient of the line segments, and hence the velocities. And so it follows that since VA and VB are unchanged as a result of the translation, the kinetic energy for each segment is unchanged, and therefore the action for each segment is unchanged. And so we can write that the total action of the translated segment, which we call S', is the same as the total action of the original untranslated segment. And it's important to note that you can repeat this process for any size of translation, characterized by A, and you will always find that the action remains invariant. It does not change, no matter whether the translation is big or small. And so this tells us that the total value of the action along both segments is completely independent of A. And the way that we're going to write this is by saying that the change in action resulting from the translation is 0. Now, to uncover momentum conservation, we're going to use a trick. Instead of shifting all 3 points all at once, we're going to perform the same overall translation in 3 sub-steps. To make it clear what we mean, consider again our 2 segments and label our 3 points 1, 2, and 3. And then let's translate these lines in the x direction. We then label the new locations of our 3 points 1', 2', and 3'. Now, we wish to investigate what happens if rather than shifting all 3 points simultaneously, we do it in 3 stages. First, we shift point 1, and we note that this will result in a change in action, which we will label delta S1. Next, we imagine shifting point 3 and note the corresponding change in action, which we label delta S3. And then finally, we shift the middle point and call the resulting change in action delta S2. Now, the net change in the action resulting from the 3 independent shifts is just the sum of the individual changes, and this must equal the total change in the action. But notice that this combined effect is exactly the same as shifting all 3 points simultaneously, and, as we've already shown, the total change in the action is 0. This therefore gives us a new condition due to translation invariance, which we can write as delta S1 plus delta S3 plus delta S2 is equal to 0. Up to this point, we have used only translation invariance. We have not used the principle of stationary action. So let's now do that. The first thing to appreciate is that if the untranslated path with endpoints x1 and x3, which we call x of t, represents the true physical path, then the translated path, which we call x prime of t, which is equal to x of t plus a, is also a true physical path corresponding to the new translated start and endpoints of the trajectory. Or to put this slightly more formally, if x of t is a true physical path between endpoints x1 and x3, then the translated path, x of t plus a, is a true physical path between the translated endpoints x1 plus a and x3 plus a. And so the entire stationary action property is preserved under translation. And so we can now make use of this fact in a rather ingenious way. If we start with our original untranslated true path, x of t, and then translate it, we end up with a shifted path which also represents a true path for the shifted endpoints. And here's the key step. Because this represents a true path, if we consider a small deviation of the translated path, which here we label eta of t, while keeping the endpoints fixed, then the corresponding change in the action will be 0 to first order. This is simply a statement of the principle of stationary action. Now let's apply the same idea to our two segments. So if we again translate first point 1, then point 3, and finally point 2, we note that the final move corresponds to an internal variation of the path, with the endpoints now fixed at points 1' and 3'. To see this clearly, notice that just before the final move of point 2, the endpoints are already fixed at 1' and 3'. The subsequent movement of point 2 therefore represents a small deviation of the interior of the actual path. And here is the crucial point. Because of the principle of stationary action, this small internal deviation of the path produces no change in the action to first order, and so we can write that delta S2 equals 0. And so to summarise, in the final step we move only the middle point, while keeping the translated endpoints 1' and 3' fixed. Because the shifted path represents a true physical trajectory, a small deviation of the interior of the path leads to no change in the action. We therefore conclude that delta S2 equals 0 to first order in A, where A represents the translation parameter, which we can take as arbitrarily small as we like. And so when the dust has settled, we end up with two conditions. First, translation invariance of the action gave the condition delta S1 plus delta S3 plus delta S2 equals 0, and then the principle of stationary action gave the condition that delta S2 equals 0 to first order in A. So let's now combine these two conditions, and we end up with the fact that delta S1 plus delta S3 is equal to 0. Our task is now to understand what this condition means physically, and to do that, we first need to answer a question. Can we express delta S1 and delta S3 in terms of derivatives? The basic idea is the same as estimating the change in height on a hill. If you know the slope and take a tiny step, then the change in height is approximately equal to the slope times the small step size. In our case, the change in action plays the role of the change in height, and this is then approximately equal to the derivative of the action with respect to the point that is moved, multiplied by the small shift A. And so, if we recall the condition that we had, which was delta S1 plus delta S3 equals 0, we can then write delta S1 equals ds total by dx1 times A, and delta S3 equals ds total by dx3 times A. And if we then sub these expressions back into our constraint equation, we find the following expression, now written in terms of derivatives of the total action. We can then cancel off the a terms and we end up with the following simple result relating the derivative of the total action with respect to the two endpoints x1 and x3. This equation is the concrete mathematical statement of spatial translation invariance for this two-segment trajectory after using the fact that the interior variation vanishes. So our next task is to figure out what these derivatives are by recalling the expression for the total action that we derived earlier. First, let's look at the derivative with respect to x1. We see that only the first term in the action contains x1, and so we can write ds by dx1 as the derivative of this first term. If we then differentiate this expression with respect to x1, we find the following result, and we notice that the term inside the bracket is none other than the velocity along segment A. And so our derivative is actually equal to the negative of the mass times the velocity along segment A. And we recognise that this is simply the negative of the momentum along segment A. Okay, so what about the derivative with respect to x3? Well, we see that x3 only appears in the second part of the action, and so we can write the derivative as the derivative of this second term. And after the dust has settled, we see that this derivative is none other than the momentum of the particle along segment B. And so to summarise, the derivative of the action with respect to x1 gave minus PA, and the derivative with respect to x3 gave PB. And if we then recall the original constraint equation and sub in our results, we see that after rearranging, we are left with the result that PA equals PB. In other words, the momentum on segment A is equal to the momentum on segment B. Momentum is conserved. Now, given that we could repeat this reasoning for every pair of adjacent small segments along the world line, we conclude that the momentum is the same at every point along the free particle's path. That's to say, the momentum is conserved. Now, it's worth just pausing for a moment and summarising how we arrived at this result, since we will follow a very similar route when it comes to understanding the conservation of energy. We began by considering a tiny segment of the actual physical trajectory and three nearby points which defined two segments, segment A and B. And we then translated these segments. And we found that as a result of the translation, the total action did not change. We then considered breaking the translation into three stages. First move point 1, then point 3, and finally the midpoint. This allowed us to write the total change in action as delta S1 plus delta S3 plus delta S2. We then used the principle of stationary action to say that for the true physical path, a small change of internal point leads to no change in the action, and therefore delta S2 equals 0. Then by combining these two conditions, we ended up with a condition on delta S1 and delta S3. We then wrote this in terms of derivatives, and when we calculated this using our total action, we found that the momentum must be the same on each segment. In other words, momentum is conserved. And so the truly remarkable conclusion is that momentum conservation isn't an extra rule we add in, rather it drops straight out of the spatial translation invariance of the action. Okay, well that's all well and good, but what about the conservation of energy? Well, the key is to ask a different question. Instead of asking, what if I translate the trajectory in space, we ask, what if I translate the trajectory in time? In other words, what if I take the entire trajectory and delay it by the same amount of time, so that every event happens a little later, but the shape of the motion is otherwise identical? If the laws of physics do not change from one moment to the next, then shifting time should not change the action. There is one important extra ingredient this time. A free particle was enough to study spatial translations, but for time translations, to see something non-trivial, we will allow the particle to possess potential energy as well. Now, for a free particle in a time-independent potential, the Lagrangian takes the following form. So let's now follow the same steps as before and consider a small segment of the particle's true trajectory. Just to remind you, if we consider a small section of the particle's true trajectory, then we can approximate a small segment with a straight line, and the velocity along this segment is constant, meaning that the kinetic energy is also constant along this section. Okay, but what about the potential energy along the segment? Well, if you think about it, the potential energy at x1 will be V of x1, and the potential energy at x2 will be V of x2. For the purposes of our approximation, we will consider the midpoint given by x1 plus x2 divided by 2, which corresponds to a potential value V of x1 plus x2 divided by 2. And we will take this as the value of the potential all along the segment. And so we have a situation in which the velocity is constant on the segment, and therefore the kinetic energy is constant, and we've also just seen that the potential energy can be treated as constant on the segment as well. As a result, we can treat the Lagrangian, which takes the following form, as constant on the segment. And so, just as we saw earlier, the action along the segment takes the following simple form, L times t2 minus t1. And if we then sub in our expression for the Lagrangian, we end up with the following equation. And this is the expression we will use for the action of a small segment of the trajectory for the case of a particle moving in a time-independent potential. Okay, so next, let's follow the same steps that we did earlier and consider 3 points that are very close together along the true trajectory. And let's then connect the points with straight lines and label the first segment A and the second segment B. We then define the potential associated with segment A using the midpoint of segment A, and the potential associated with segment B using the midpoint of segment B. We can then use our earlier result to immediately write down the action for segment A and the action for segment B, where the first terms represent the kinetic energy along the segment and the second terms the average potential energy along the segment. The total action is then given by the sum SA plus SB. Okay, so now that we have an expression for the total action, the next question is, what happens if we translate time? In other words, what happens if we let t go to t prime, where t prime is equal to t plus b? And we can visualize this time translation. If we consider our 3 points along the true trajectory as before, then when we translate the path through time by an amount equal to b, then we see that the x-coordinate remains unchanged, but the time coordinates are shifted by b. Now, if we return to the unshifted path, we can label the time duration for segment A and segment B in the following manner. After translating the path, it's clear that the duration for each segment has not changed. To see this explicitly, we can label the new time difference of segment A as t2' minus t1' and of segment B as t3' minus t2'. And then, given the definitions of t1', t2' and t3', we see that when we expand out the differences, the b's cancel and we end up with the same time differences that we started with. And so the key point is that every time difference is unchanged by this shift. And likewise, if we look at the space differences along each segment, then we see that these also remain unchanged. And we can summarize this by saying that x1' equals x1, x2' equals x2, and x3' equals x3. And so to summarize, we see that the time durations for segment A and B are unchanged by the shift, and the position differences are also unchanged as a result of the time translation. And therefore, because the action for the shifted segments only depends on space and time differences, it follows that the actions along the shifted segments are exactly the same as the actions along the unshifted segments. And so we can write that SA' equals SA and SB' equals SB, and therefore the total action is unchanged. And the way that we're going to write this is to say that the change in the total action as a result of the time translation is 0. This is simply telling us that if we translate our path through time, then the total action does not change. We say that the action is time translation invariant. But now we're going to use the same trick that we used earlier, and we're going to perform the translation in 3 sub-steps. As before, we begin by translating the first point, and we label the corresponding change in action delta S1. We then translate point 3 and label the change in action delta S3, and then finally we translate the middle point and label the resulting change in action delta S2. It then follows that the total change in action resulting from the time translation is simply the sum of these three terms, and as we've just argued, this total change is equal to 0. And so we now have a constraint equation as a direct consequence of the time translation invariance of the action. The next step is to use the principle of stationary action in the same way as earlier to show that delta S2 equals 0. To do that, we consider the situation where we have translated point 1 and point 3 but are yet to translate point 2. Then we have a situation where the endpoints are now fixed at points 1' and 3', and moving point 2 corresponds to a small deviation of the interior of the path. And according to the principle of stationary action, if the path between the fixed endpoints represents a true physical path, then a small deviation of the interior of the path should cause no change in the action to first order, which is to say that delta S2 equals 0. And so we end up with two conditions, the first resulting from time translation invariance of the action, and the second resulting from the principle of stationary action. And if we combine these two conditions, we end up with the constraint condition delta S1 plus delta S3 equals 0. And just as we did when considering spatial translations, we can now express delta S1 and delta S3 in terms of derivatives, and this then allows us to rewrite our constraint condition. So our next task is to calculate these derivatives by referring to the equation for the total action that we derived earlier. If we start by considering the derivatives with respect to t1, then we see that this will only act on the first two terms in the action, since these are the only terms that contain t1. And so we can write the derivative with respect to t1 of these terms. And if we carefully differentiate the terms inside the bracket, then we find the following two terms. And we note that the term inside the bracket is none other than the velocity along segment A. And so we see that these two terms can be written as half mv squared plus va, which is simply the kinetic energy on segment A plus the potential energy on segment A. And so these two terms represent the total energy of the particle along segment A. So we see that the derivative of the total action with respect to t1 gives the total energy on segment A. So what about the derivative of the action with respect to t3? Well, if we look at the total action once again, then we see that this derivative will only act on the last two terms, as these are the only terms that contain t3. And so we need to calculate the following derivative. If we carefully differentiate the terms inside the square brackets, we find the following result, which represents the negative of the total energy of the particle on segment B. So we can write that ds total by dt3 is equal to minus EB. If we then recall the constraint equation that we derived earlier and sub in our result, we find that EA minus EB is equal to 0. In other words, we can write EA equals EB, and we see that the constraint equation means that the total energy on segment A is equal to the total energy on segment B. In other words, energy is conserved. And the deep reason for this conservation of energy is because the action is invariant under translations in time. And when you combine that with the principle of stationary action, which kills the interior contribution of our three-stage translation, then the only surviving effect is a boundary term equality. And that condition gives rise to a conserved quantity, which in the case of time translation invariance is the energy. So let's zoom out and say what we have actually done in this video. We started with a symmetry of the action, and we watched a conservation law fall out of it. In the case of spatial translation symmetry, we found that momentum is conserved. And in the case of time translation symmetry, we found that energy is conserved. And this is not a coincidence. What we've uncovered is just the simplest example of a far deeper and more general result. That every continuous symmetry of the action produces a conserved quantity. This single sentence is the essence of Noether's theorem, proved in 1918 by the groundbreaking mathematician Noether. In its full power, Noether's theorem goes much further than what we've seen here today. It applies not just to classical particles, but to quantum fields that fill all of space. In modern physics, This single idea underlies everything from electromagnetism to quantum field theory, where symmetries don't just constrain motion, they help determine the very forces that exist. The story of Emmy Noether is extraordinary. She produced mathematics so original and so powerful that it reshaped the very foundations of modern algebra and theoretical physics. And yet for years she was blocked from a normal academic career simply because she was a woman. In Göttingen, she even lectured under other people's names before being allowed to teach officially. Later, because she was Jewish, she was forced out of her position in 1933 and left Germany for the United States, where she continued teaching and working until her death in 1935. After she died, Albert Einstein wrote in the New York Times, "In the judgment of the most competent living mathematicians, Fräulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began." And the remarkable thing is that Noether's theorem is not just a beautiful result, it acts as a guiding principle for uncovering the laws of nature. For example, we have seen that the conservation of momentum results from space translation symmetry, and the conservation of energy from time translation symmetry. But what symmetry is responsible for the conservation of electric charge? The fact that the total amount of negative and positive charge appears to remain constant in the universe? The answer to that question, and the deep role Noether's theorem plays in determining the structure of the standard model of particle physics, will be the subject of the next video in this series. So until next time, goodbye. And as always, a massive thank you to all my patrons, and a special shout out to the following who have been incredibly generous with their support. Thank you so much, I couldn't do it without you.